Grounding capacitors is essential for safety and proper operation, and the National Electrical Code, specifically Section 460.10, provides guidelines for achieving this. According to Section 460.10, there are two primary methods for grounding capacitors. Firstly, you can ground the capacitor directly to the grounding electrode conductor, often referred to as the GEC of the system. Secondly, you can ground the capacitor through the equipment grounding conductor, often referred to as the EGC, of the circuit that supplies power to the capacitor. Choosing the appropriate method depends on the specific installation and system configuration. The conductor used for grounding the capacitor must be sized appropriately. The code stipulates that the grounding conductor size must be equal to or greater than the largest ungrounded conductor connected to the capacitor. This requirement ensures that the grounding path can safely handle any fault current. When grounding a capacitor directly to the GEC system, the grounding conductor should be connected to the grounding electrode conductor at the service entrance or at the main bonding jumper. This provides a direct and low impedance path to ground, enhancing safety. If you choose to ground the capacitor through the EGC of the circuit, the grounding conductor must be connected to the EGC of the circuit supplying the capacitor. This method relies on the integrity of the EGC pathway back to the source. In many installations, capacitors are mounted within a metal enclosure or chamber. In such cases, it's essential to bond the capacitor to this enclosure. This bonding is typically accomplished using a bonding jumper. The size of the bonding jumper should be equal to or greater than the size of the grounding conductor to ensure effective fault current handling. Now let's consider an example involving a 400 Hz system. In this scenario, the capacitor is used on the secondary side of a 208 and 120 volts transformer. You can ground the capacitor either directly to the GEC of the 208 and 120 volts system or through the EGC of the circuit supplying the capacitor from the 208 volts to 208 and 120 volts transformer. It's also indicated a number 4 American wire gauge conductor or larger must be used to ground the capacitor, assuming it is the largest ungrounded conductor connected to the capacitor. Let's delve a little deeper into the requirements and considerations. Firstly, considering the grounding electrode conductor. The grounding electrode conductor is a critical component of the electrical system, connecting the system's grounded conductor, typically the neutral, to the grounding electrode. The grounding electrode is a buried metal object, such as a ground rod or metal water pipe that provides a direct connection to the earth. Grounding to the GEC offers a low impedance path for fault currents, helping to quickly trip over current protection devices like circuit breakers or fuses, thus minimizing the risk of electrical shock and equipment damage. Secondly, the equipment grounding conductor provides a path for fault current from equipment enclosures and other non-current carrying metal parts back to the source. This path is essential for safety, as it helps to ensure that exposed metal parts do not become energized during a fault. When using the EGC to ground a capacitor, it is crucial to verify that the EGC pathway is continuous and properly sized to handle potential fault currents. Now consider the conductor sizing and NEC tables. Determining the correct conductor size for grounding capacitors involves referring to NEC tables and considering the specific characteristics of the circuit. Table 250.122 in the NEC is commonly used to determine the minimum size of equipment grounding conductors based on the rating of the overcurrent protective device in the circuit. When selecting a grounding conductor, you must ensure that it is suitable for the available fault current and that it has adequate ampacity to carry the fault current without overheating. Also, the bonding jumpers play a vital role in maintaining a low impedance path for fault currents. These jumpers connect metal enclosures, equipment frames, and other non-current carrying metal parts to the grounding system. Proper bonding helps to prevent voltage differences between metal parts, reducing the risk of electric shock. The NEC provides guidelines for sizing bonding jumpers, and it is essential to follow these guidelines to ensure effective bonding. As for the 400 Hz systems, grounding in these systems may have unique considerations compared to typical 60 Hz systems. The higher frequency can affect impedance and skin effect, potentially influencing grounding performance. It's important to consult with qualified electrical engineers and adhere to relevant industry standards when designing grounding systems for 400 Hz applications. Finally, let's consider the inspection and maintenance. Grounding systems should be inspected and maintained regularly to ensure their continued effectiveness. Inspections should include visual checks for corrosion, loose connections, and damaged conductors. Testing may also be necessary to verify the integrity of the grounding path and to measure ground impedance. Regular maintenance can help to identify and address potential issues before they become safety hazards. Grounding electrode conductors should be connected to the grounding electrode at the service entrance or at the main bonding jumper. This ensures a direct and low impedance path to ground, which is essential for safety. It's important to avoid creating unnecessary bends or loops in the grounding conductor, as these can increase impedance and reduce the effectiveness of the grounding system. Also, grounding through the equipment grounding conductor relies on the integrity of the EGC pathway back to the source. The EGC should be properly installed and maintained to ensure a continuous and low impedance path for fault currents. Common grounding mistakes include using undersized conductors, neglecting bonding requirements, and failing to properly maintain grounding systems. These mistakes can compromise the effectiveness of the grounding system and increase the risk of electrical shock and equipment damage. In addition to complying with the NEC, it's essential to follow industry best practices for grounding. This may involve consulting with experienced electrical engineers, using high-quality grounding products, and implementing comprehensive grounding testing programs. Understanding the principles of grounding and following relevant codes and standards are crucial for ensuring electrical safety and equipment protection. When in doubt, consult with a qualified electrical professional. Additional considerations include grounding electrode system, supplementary electrodes, and grounding impedance. Firstly, the grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or metal water pipes, that are used to establish a connection to the earth. The NEC specifies requirements for the type, size, and installation of grounding electrodes to ensure that they provide an effective path to ground. Secondly, in some cases, it may be necessary to install supplementary grounding electrodes to improve the overall grounding performance of the system. Supplementary electrodes can be used to reduce ground impedance and to provide a more robust grounding path in areas with poor soil conductivity. Thirdly, grounding impedance is a measure of the opposition to the flow of fault current through the grounding system. Low grounding impedance is essential for effective grounding, as it helps to ensure that fault currents can quickly and safely return to the source, stripping of current protection devices and minimizing the risk of electrical shock. Methods for reducing grounding impedance include using larger grounding conductors, installing supplementary grounding electrodes, and improving soil conductivity. Ground fault protection is a critical safety feature in electrical systems that helps to detect and interrupt ground faults. Ground fault protection devices, such as ground fault circuit interrupters, often called GFCIs, and ground fault relays, are designed to monitor the current flowing in the circuit and to quickly trip the circuit if a ground fault is detected. Ground fault protection can significantly reduce the risk of electrical shock and equipment damage. Surge protection devices, often called SPD, are used to protect electrical equipment from voltage surges caused by lightning, switching transients, and other disturbances. SPD work by diverting excess voltage to ground, preventing it from damaging sensitive electronic components. Proper grounding is essential for the effective operation of SPD. Electrical noise can interfere with the operation of electronic equipment and cause data errors, communication problems, and other issues. Proper grounding can help to reduce electrical noise by providing a low impedance path for noise currents to return to the source. Shielded cables, filters, and other noise reduction techniques can also be used in conjunction with grounding to minimize electrical noise. Static electricity can accumulate on non-conductive surfaces and discharge suddenly, causing damage to electronic equipment and posing a fire hazard. Proper grounding can help to dissipate static electricity, preventing it from accumulating to dangerous levels. Static dissipative materials, grounding straps, and other static control measures can also be used to minimize static electricity. In hazardous locations, such as those where flammable gases or vapors are present, special grounding requirements apply to minimize the risk of explosion or fire. These requirements typically involve the use of intrinsically safe equipment, explosion-proof enclosures, and other specialized grounding techniques. The NEC provides detailed guidance on grounding in hazardous locations. Lightning protection systems are designed to protect buildings and structures from lightning strikes. These systems typically consist of air terminals, down conductors, and a grounding electrode system that work together to safely conduct lightning current to ground. Proper grounding is essential for the effective operation of lightning protection systems. Common grounding system configurations include single-point grounding, multi-point grounding, and hybrid grounding. Single-point grounding involves connecting all ground connections to a single point, typically at the service entrance. Multi-point grounding involves connecting ground connections to multiple points throughout the system. Hybrid grounding combines aspects of both single-point and multi-point grounding to achieve optimal performance. The choice of grounding system configuration depends on the specific application and the characteristics of the electrical system. Grounding system testing involves measuring ground impedance, continuity, and other parameters to verify the integrity of the grounding system. Testing should be performed during initial installation and periodically thereafter to ensure that the grounding system continues to meet applicable codes and standards. Common testing methods include the 3-point fall of potential test and the clamp on ground resistance test. Grounding documentation should include detailed information about the grounding system, including conductor sizes, grounding electrode locations, bonding connections, and test results. This documentation is essential for troubleshooting, maintenance, and future modifications to the electrical system. Proper documentation can also help to ensure compliance with applicable codes and standards. In conclusion, grounding is a critical aspect of electrical safety and equipment protection. Understanding the principles of grounding, following relevant codes and standards, and implementing proper grounding practices are essential for ensuring the safe and reliable operation of electrical systems. When in doubt, consult with a qualified electrical professional.